So you got a big problem. I want you to do this on your own. Okay, this you've got 4 spans. EI is constant. You have an axis of symmetry through C, so you can simplify the problem. So this is one example where the axis of symmetry passes through a support. So I have shown you this axis of symmetry, and the reflected shape will be symmetrical. And this is very easy to do because you can cut the beam exactly at the axis of symmetry, separate them out, and when you do that, you get back a problem which we have solved in the last session. So there's nothing much to do. We've already solved this problem. This is an example when the axis of symmetry passes through a support. Let's take another example. Let's say the axis of symmetry passes through the middle of a beam. Now you know what to do in such cases also. You have to replace that cut location with what is called the guided fixed support, because you know for sure whenever you have an axis of symmetry, you cannot have a slope there. If you had a slope, it would have to be clockwise or anti-clockwise, and that would violate symmetry. So the only way you can have preserve symmetry is by having a zero slope at the axis of symmetry. You may have a deflection or you may not have a deflection. If you don't have a vertical support there, you won't have a deflection. Here you have no vertical support there, so you have a deflection delta B, and you don't get a vertical shear there, and so this becomes your problem. Okay, so you can simplify it with a guided fixed support, and you know the stiffnesses of a guided fixed support. We saw this in today's session. Now the slope distribution equations, only theta into theta A, and for BA minus EI by theta A. If you do it this way, you can do it much faster than any other method. So we are trying to take advantage of symmetry, reduce our degree of kinematic indeterminacy, and solve the problem much faster. Now the question is, how do we find fixed end moments in beams with guided supports? Let's say you have a problem like this. How do you find fixed end moments? We have tables for regular beams with both ends fixed. So any suggestion how to crack this one? If both ends are fixed and you have intermediate loading in the beam, you know there are tables and you can use conjugate beam method and find the fixed end moment. How do you find fixed end moments in situations like this? Not difficult. What should you do? Any answers? All you have to do is to double this beam. Okay, that's it. So you've got the fixed beam. Of course, with this funny loading, but you should know how to handle this loading. Go back to the double beam with the full loading and work out the fixed end moments, and then use the same fixed end moment MF, in this case MFAA dash, and that's your MFAB. Okay, so this is the bending moment diagram you get for such a beam, the fixed end moment. Okay, so you'll also get a fixed end moment at the guided fixed support. Please note, it's a sagging moment. Okay, so in this fixed beam, you get two moments. You get M1 and you get M2, and you have to plug in those values in your fixed beam. Okay, let's take an example. If you had a beam like this, how do you get fixed end moments? Double the beam, same loading, double the span. Your fixed end moments are easily obtainable. You draw the bending moment diagram for the fixed beam. MFAB is Q into 2L the whole squared by 12 with a minus sign, and MFBA is what you get at the midspan of the fixed beam, which is nothing but the bending moment in the simply supported beam, which is Q into 2L the whole squared by 8 minus the fixed end moment, right? This is the only extra effort you need. which is q into 2L the whole squared by 24. So if you know how to get these two fixed end moments, you can solve it, any problem. Let's take this problem, okay? It's the same problem as we did earlier, except that there's no support at C. How do you do this problem? Very interesting. Give it a shot. First, take advantage of symmetry, which means you cut the beam at the axis of symmetry and put guided fixed supports there. That's your first step. How many unknowns? What's the degree of kinematic indeterminate? It's very simple. The unknown. AB and MFBA are concerned, it's very easy. You know that. Do it. Now you tell me how to find out MFBC and MFCB. Well, it's good to draw the picture of the double beam. Okay, BCB dash. That's your loading, and you need to find the fixed end moments. Okay, you know the formulas due to any one load. Due to 80 kilonewton, use the formula WAB squared by L squared, and from the other load also use the same formula with the correct sign. And in this case, A is 0.5 meters and B is 3.5 meters because your total span is 4 meters. So see carefully what we've done. MFBC is minus of 80 into 0.5 into 3.5 the whole squared by 4 squared. That's what you get from the first 80 kilonewton loading. From the second 80 kilonewton loading, you get an additional fixed end moment where A and B get interchanged. That's all. That's all you have to do. And you have to press your calculator buttons and get the correct answer. Minus 35. You also have MFCB. How do you get MFCB? Well, for this, supposing this beam BCB dash was simply supported, can you not find the bending moment at C? That moment minus a fixed end moment is the net moment there. It's a sagging moment, which means it's going to be anti-clockwise, and you can prove that that moment turns out to be minus 5.0 kilonewton. Needs a little thinking. All shortcuts in structural analysis are good to take, but if you know the subject properly, it's simplified everything. Okay. You've got MFBC, you've got MFCB, you're now in a position to crack this problem. How? Next step. So write down your fixed end moments and then write down your slope deflection equation. Remember, for AB the equations are the same as what we did earlier, but for BC remember the equations because you got a guided fixed support here. MFBC is MBC is MFBC plus EI by L theta B, and MCB is MFCB minus EI by L theta B. That's the only change. It's a change in your slope deflection equation. It's a change you need for taking advantage of the unknown deflection at C that you don't need to know. It's a powerful method. That's it. Your only unknown is theta B. Substitute your values of fixed end moments. You got these 4 equations. Now invoke the equilibrium equation. What is the equilibrium equation? Equilibrium equation. This is the matrix. For the free, it's enough to draw for one half and then draw a mirror image for the other half. So this problem looks complicated, looks difficult, looks scary, but it reduced to a single unknown problem. You have to be smart to do it this way. Very quick way of solving the problem. So, any questions? Please speak up. This is your last chance. We have half an hour left. I want to have an interaction before I proceed. Any question? Now let's have an interaction. We have some time, so before I do the last part, I want to have some. Yes?
Hello. Hello.
Yes, go ahead. Yes.
Good morning, sir.
Good morning.
Sir, the session is very good. So the session is very good, and we are from mechanical, and we just want to know the derivation to calculate the m. That is 4EI upon L into theta A plus 2EI upon L into theta B. Then from where this derivation comes, sir? We are from mechanical, and this slope and deflection method is just new for us.
Okay. Okay.
Sir, this student's query.
I will answer that. I covered it in my slides. But let me go back to those slides and answer that. Any other question? I'll answer your question for sure today. Any other question?
This is only the question that the student want to ask from you.
I will answer. I will answer. Any other question?
No, sir.
Okay. Let
No,
me
sir.
go back. Thank you. Multi-span continuous beam. We said that the deflected shape may look like this. You have two unknown rotations, theta A and theta B. You have n moments MAB and MBA, and we want to write down equations that relate MAB, MBA with theta A and theta B. Is that clear? Very simple. We do this by what is known as the method of superposition, which is applicable when the structure behaves in a linear elastic manner. That's a fundamental assumption. So the first thing we do is we arrest the unknown rotations theta A and theta B, and we fix the ends at A and B. Okay, and we must be able to get the fixed end moments. I presume you understand how we've done that, MFAB and MFBA. Now, what do we do next? What we do next is we take the fixed beam and we now allow a theta A to take place. The best way to understand is the fixed end A somehow rotates like this, it slips and undergoes the rotation theta A, only theta A, theta B is still 0, and this is going to be a deflected shape. Now, due to this, you need to now analyze this and find out that the moment you get at the two ends are 4 EI by L theta A and 2 EI by L theta A. This is a very important proof. It's something that we taught in an earlier session. Why is it 4 EI by L and why is 2 EI by L? It can be proved easily. How do we prove this? This also we had proved. Let me go back. Yeah. Okay. If I have a beam like this and I apply a moment m0 at one end, do you all agree that you can prove this to be 3I by theta naught? I want to go back to that girl to ask this question. I want to dialogue with you. Whoever asks this question, can I go back?
Hello, yes sir, I can prove it by using equation.
Lady who asked. Okay, there are many ways
Hello,
of doing it.
yes sir, I can prove it by using Macaulay method, by using Euler
That's a
equation.
tougher method. There is a simple method called conjugate beam method.
That is slope dy by dx
theta. Method where you can prove it very easily. Yeah. So all you have to do, all you have to do is to draw that bending moment diagram. It's a triangle, and then put that diagram, divide by EI. That will be your curvature diagram, and find the reactions at the two ends. You can. Those reactions will be your slope. So you'll get this relationship m0 is equal to 3I by L into theta naught. Do you know how to do that?
Yes, sir.
Okay. Okay. Now.
Yes, sir.
Follow carefully. Now we are trying to fix the end A so that the slope there is 0. Okay.
Okay, sir.
To do that, you have to now apply a clockwise moment. Here. You have to apply a clockwise moment the way I'm going to show you now. You remember what I did on the board?
Yes, sir.
It's here. If you apply a moment here, then this relationship you know? Yes or no? So what we wanted to do was we wanted to apply a moment here so that this theta okay.
Yes,
this is the same relationship. Now you have to make sure that in your previous diagram, whatever theta you get is eliminated because of this moment. And if you add up those two moments, you can prove, and I want you to do this on your own to check out, you can prove that the net moment you get is is 4 EI by L. That's the proof. So will you go through this? You will find that, okay, the other thing is intuitively I want you to know that when the other end is fixed, it's more difficult to rotate. That's why you get a higher stiffness. The 3 EI by L goes up to 4 EI by L, and this is the bending moment diagram you get. So my request to you, if you've not understood this, derive this and get this very clear, that if I have a situation like this, apply a clockwise moment m0 here, I'm going to get a deflected shape like this. The stiffness is 4 EI by L into theta naught, and the moment that carries across to the fixed end at the other end is m0 by 2. This is something fundamental. This is the bending moment diagram you get. So with this,
Okay, sir.
with this, you have to go back and learn this. With this, you come back to this derivation, and that's how you get these two properties. Now, when you
Okay.
add up everything by superposition, you
Thank you, sir.
get MAB is equal to MFAB plus 4EI. MFA can do anytime. Okay. Try doing this problem. This is a symmetric portal frame subject to a uniformly distributed load and a concentrated load at the midspan. How do you analyze this structure? It looks difficult, but I can assure you it's not if you take advantage of symmetry. How do you analyze the structure? Well, first you try to draw the deflected shape and take advantage of the symmetry, and you'll find that the deflected shape is more or less like that. Agreed? Theta A is 0, theta E is 0. There is no sway because of symmetry, and your only unknowns are theta B and theta D, and they have to be equal and opposite to preserve symmetry. Now, you can take advantage of symmetry, cut the section at C where the axis of symmetry is there, and you have to put a guided fixed support, which means you're cutting through that 200 kilonewton load so that you have 100 kilonewton on either side. You can choose either the left side or the right side, whichever you like. I've chosen the left side. So your problem is now reduced to this problem. A, B, C. I've thrown away C, D, E. I made it simple, but I've introduced a correct boundary condition. Single unknown, theta B. EI values as given in the original problem. First, fixed end moments. Okay, how do I get the fixed end moments? Now there are two loads. Remember, to get fixed end moment, it's better to go back to the original beam, the double beam. So in the columns you don't have any fixed end moment, but in the beams you have MFBC due to the UDL and due to the concentrated load. Take the full span of the beam 6 meters. So it's minus 50 into 6 squared by 12 minus 200 into 6 by 8. That's the formula for fixed end moment. And once you have MFBC, you can have MFCB also. Remember how to do that? Get the sagging moment in the simply supported beam and subtract the fixed end moment and put a negative sign because it's anti-clockwise. This you must be able to do. So I've got MFBC as minus 300.0 kilonewton meter, MFCB as minus 225.0 kilonewton meter. I hope you're with me. MEI by L into theta B and minus EI by L into theta B. Remember, here the EI is 2 EI because your beam is stiffer than your column, and your span is for the beam 3 meter. You must correctly do that, and then simplify it. You find that you've got these 4 equations. If you know theta B, you can crack the problem very easily. To get theta B, you need one equilibrium equation, and that equilibrium equation is very easy to get. That is MBA plus MBC is 0. So you add the second and third equations, solve it, plug it into your solution. You've got the end moments. Okay, that's it. It's as simple as that. Now you draw the free body for the full beam, full frame. You've got the end moments. Okay, you can draw it for all, you need not draw for half the frame, draw for the entire frame. And then you can find the shear forces in your beam, put them as axial forces in the columns, find the shear forces in your column by adding the two moments and dividing by the height of column, and putting those as axial forces in your beam. And that's it, you finished it. So after the free body diagram, you can draw the axial force diagram. You'll find you have compression in all the three members. You can draw the shear force diagram, and you can draw the bending moment diagram. Very interesting that whenever you have problems of this kind where only the beam is loaded and the column is not loaded, you'll find the fixed end moment at the base of the column will be half the moment that you get at the joint. Okay, so you had 180 kilonewton meter at the joint on top, you get 90 kilonewton meter, and this is the deflected shape. You see how this matches the deflected shape. Wherever in the beam you have sagging in the middle region, you have positive moment, you have hogging, you have negative moment, and so on. And the point of contraflexion in the column will be at 1/3 height. I'm ending this session with an assignment for you to do, a homework assignment. Take a look at this frame, do it on your own, and we will give you the solution later. Okay, right, now just take this down. Now I am ready to take any questions. We have enough time. We've got 15 minutes to take all your questions. Let's go ahead. Two questions are there. Let me see. In example number 4, at point C, there is a simple support. Then why do you consider it as a fixed support? Can I speak to the person, whoever asked this question? Can you see this picture? At C, there is no support. So what we are saying is, that's an axis of symmetry. It's cutting through the middle of the beam. This is a support that you have to give to capture the deflected shape. Okay. I hope that clarifies your. Okay, let's go back, and maybe you had a doubt here. See, there are two types of symmetry problems. This is one type in which you have a support at C, and you can't call that a simple support. That's a support over which the beam is continuous. Here, because the slope at C is 0, you can cut it there and then you put a fixed support there. Is it clear? This is not example 4, this is some other example which we solved earlier. The other type of problem is, like here, at this location you don't have a support. There the guided fixed support is appropriate, and example 4 belongs to this category. So I hope this answers your question. Let's go back to, you see, we are learning a new topic and it's best to go slow. But it's good to ask the questions you're asking. But that's too advanced at this stage. We are going slow. We are doing this in 6 hours, in three 2-hour modules. In the first module, we took the simplest cases where you had only theta. Theta A, theta B, theta C, theta D. You had no delta. In a non-prismatic beam, you have at the junction of the two prismatic elements, you have a joint, you have a node, and at that node you have to take care of delta in addition to theta. So that belongs to the third category, which we'll cover day after tomorrow, applications to problem with unknown joints way. We will do the problem that you are asking. How do you deal with problems where you have non-prismatic conditions? But today we don't do that. Tomorrow also we don't do that. We'll do it in module 3. Have you done slope deflection method in your college? Normally they do it little differently. They cover everything in one shot, not slowly and steadily like this. See, usually structural analysis takes a little time to master. We've seen our students have difficulty drawing bending moment diagrams. So first you have to be very strong with statically determinate beams, drawing free body diagrams, drawing bending moment diagrams, drawing shear force diagrams, drawing deflected shape. That's what I've covered in parts 1 and 2 in my book. Then you learn how to calculate deflections and slopes of statically determined beams. That's part 4. Different ways. An advancement of slope deflection method, stiffness method, okay, where you generate what is called the stiffness matrix, which you also are getting accidentally when you are trying to solve the equilibrium equations in the slope deflection method. In the moment distribution method, you don't solve these equations explicitly, you do what is called a relaxation method of solving them. And it's good to learn the moment distribution method after you learn the slope deflection method, though in some colleges I understand you do it first. We're going to meet tomorrow, same time, 10 o'clock. I want to give you a hint about what we're going to do tomorrow. Today we did one problem with two unknowns, theta b and theta c, remember? There at C you had a roller support. Now, we actually did a lot of extra work because at that support we know the moment is 0. So, we found out theta c only to prove that MCB is 0. Why not take advantage of that knowledge? When you take advantage of that knowledge, you can reduce your degree of kinematic indeterminacy. For that, you have to modify the slope deflection equations to take advantage. We'll look into this tomorrow. I want you to know all the shortcuts. If you don't want to take the shortcut, you can do it the hard way. That also is possible, but it will take you more time. We have a couple of minutes. Okay, these video lectures have been recorded. They will be available. You can go through it anytime. I believe they'll be cut into 15-minute slots or so. You'll have a lot of time to go through it in greater detail and to understand. And you are always welcome to write to me. I'll write my email ID on the board. Any query, you can write to me and I will try to answer them if possible in the next class. So you can write to this email ID with your query. Then I look forward